Hey everyone, and welcome to this explainer. When we look up, it's just so incredibly easy to think of the atmosphere as, well, just empty space. But actually, scratch that. It isn't empty at all. It's a highly dynamic, beautifully layered ocean. And you and I, we're walking around right at the very bottom of it. So today, I want to enthusiastically invite you on an upward, vertical journey. We're going to travel straight up from the ground beneath your feet all the way to the absolute edge of outer space, just to truly understand this invisible ocean that makes our lives possible. Which brings us to the big question: what exactly is the sky made of? It's a simple question, right? But the answer is remarkably complex. Okay, let's dive into this, because the actual recipe of the air we're breathing right this second is literally full of surprises. Here's our flight itinerary for today. First, we'll look at the recipe for air. Second, we'll take a journey into the sky. Third, we'll examine two spheres of chemistry. And finally, we'll look at how we change it. Let's get going. Section 1. The recipe for air. Before we actually go up, we need to know what we're swimming in right now, down here at the surface. And this brilliantly illustrates how nitrogen makes up a staggering 78.08% of our air by volume. Oxygen comes next at 20.95%. So together, they're nearly the entire pie. But what really stands out here is carbon dioxide. Despite how much we talk about it, it represents exactly 0.036%, just a tiny fraction. The rest of the air is just trace gases, things like argon, neon, helium, and hydrogen. But hold on, gases aren't the whole story. The air is actually full of solid matter, specifically dust particles. Now, you might think of dust as just a nuisance you have to clean off your bookshelf, but up in the atmosphere, it's sheer magic. These particles have a higher concentration in subtropical and temperate regions, largely carried there by dry winds. So why are they magical? Well, they provide the absolutely crucial nuclei that water vapor needs to form clouds. Without dust, our entire weather system just breaks down. Plus, it's the scattering of light by these very dust particles that makes our sky blue during the day, and they even dictate the duration of twilight after the sun goes down. Then we have water vapor, which is, well, highly variable. Down in the warm tropics, it can account for up to 4% of the air by volume. But if you travel to a desert or to the polar regions, that number drops to less than 1%. And this is because moisture holding capacity is directly proportional to temperature. Warmer air simply holds more water. But regardless of where you are, this water vapor acts like a critical thermal blanket. It absorbs heat and literally prevents the Earth from experiencing wild, extreme temperature swings. Section 2. Journey into the sky. Okay, imagine we're stepping into a giant glass space elevator. The doors close, and we begin our literal ascent through the troposphere. This is our home. It's the lowermost layer, averaging about 13 kilometers in height. Though it does vary, it extends to just 8 kilometers near the poles and bulges out to about 18 kilometers at the equator. This layer is bustling, chaotic, and super weather heavy. Literally every single climate and weather change you've ever experienced takes place right here. As our elevator climbs higher through the troposphere, things get chilly very quickly. For exactly every 165 meters of altitude we gain, the temperature drops by exactly 1 degree Celsius. This highly predictable lapse rate is the exact reason why, even in super warm climates, towering mountain peaks are perpetually capped with snow. Let's move to and see how this builds. As we cross the boundary known as the tropopause, we enter the stratosphere, which extends up to 50 kilometers. Suddenly, the chaos of weather is just gone. It's completely cloud-free, making it the ideal, absolutely smooth place for flying big commercial planes. Interestingly, temperature behaves totally differently here depending on the season, increasing during the summers and decreasing during the winters. It also holds the highest concentration of ozone, known as the ozonosphere, which acts as our planet's giant sunscreen. Going even higher, we plunge into the mesosphere, extending from 50 to 80 kilometers above the Earth. Here, the temperature rules flip yet again. The higher we go in the mesosphere, the colder it gets, ultimately making this the absolute coldest layer in the entire atmosphere. It essentially acts as a freezing, invisible barrier high above the stratosphere. Now things get extreme in the thermosphere. Stretching from 80 to 400 kilometers, the air is incredibly thin, and the temperature rapidly skyrockets as we climb, eventually hitting a massive 1,500 degrees Celsius. Now, what's really interesting about this slide is how this scorching layer is actually our ultimate planetary shield. It literally protects the Earth from incoming meteorites and even the remains of abandoned satellites. And because it contains electrically charged particles, it serves an amazing communication function. It reflects radio waves from Earth right back down to us. That electrically charged zone within the thermosphere, that's called the ionosphere. The ionization here happens mainly because of intense ultraviolet, X-ray, and gamma radiation from space. It's actually divided into highly specific layers, neatly labeled D, E, F1, F2, and G. And here's a truly fascinating fact for you. The D and E layers are completely dependent on the sun. They exist only during the daytime, completely vanishing as soon as the sun sets. No sun, no D and E layers. Finally, our elevator breaches 400 kilometers and enters the exosphere. This is the uppermost limit. The atmosphere here is exceptionally thin, largely home to the lightest gases, namely helium and hydrogen. Temperatures here just continue to climb, potentially crossing a blistering 5,000 degrees Celsius. From here, stretching thousands of kilometers out, the exosphere slowly, quietly merges with the sheer void of outer space. Section 3. Two spheres of chemistry. Now that we've mapped the sky by temperature, let's do a quick zoom out. According to the International Space Symposium, the entire atmosphere can be sliced into two broad chemical layers. The lower layer is the homosphere, stretching from the surface all the way up to 88 kilometers. This encompasses the troposphere, stratosphere, and mesosphere we just visited. Its defining feature is that the proportions of component gases are beautifully uniform and well mixed. But beyond 88 kilometers lies the heterosphere. Encompassing the thermosphere and beyond, this upper layer is totally non-uniform in its chemical composition. That well-mixed air we rely on down here is replaced by separated, distinct layers of gases up there. Section 4. How we change it. For our final section, we need to bring our space elevator crashing back down to Earth's surface. Having explored the mechanics of the system, we really must neutrally examine how our own chemical additions are altering the atmosphere. Take air pollution, for example. When we add sulfur dioxide and nitrogen oxides, they form sulfuric and nitric acids, resulting in acid rain that harms plants, fish, and buildings. Then you have global warming, driven by greenhouse gases like carbon dioxide, methane, nitrous oxide, and water vapor trapping heat. We also face separate issues with ozone, which we'll look at in a second. So the crucial point is to cleanly separate these mechanics, because acid rain is a completely different chemical reaction than the greenhouse effect. When discussing greenhouse gases, the data points to a very specific and quite surprising industrial culprit, SF6. While carbon dioxide gets all the headlines, SF6 is actually the most potent greenhouse gas in existence. It's widely utilized in heavy infrastructure, specifically in things like circuit breakers and gas-insulated substations. It's a stark reminder that some of our most impactful changes to the atmosphere actually come from incredibly niche industrial applications. Finally, we encounter what we can call the ozone paradox. Up in the stratosphere, ozone is vital. But human-made CFCs, cooling fluids used in refrigeration, are carried by winds all the way to Antarctica, where they get trapped in the cold air by the polar vortex, severely depleting this protective layer. However, down here at ground level, ozone is actually a destructive pollutant. When sunlight interacts with hydrocarbons and nitrogen oxides at the surface, it forms tropospheric ozone. This ground-level ozone damages vegetation, injures living tissue, causes respiratory problems, and literally destroys materials like nylon and rubber. It's the exact same chemical, but it has an entirely different impact depending on which layer of the ocean it resides in. And that brings our journey to an end. We've seen that the sky is definitely not empty space. It's a precisely balanced mixture of gases and dust divided into distinct, vital layers that dictate our weather, protect us from radiation, and even shield us from meteorites. We live at the very bottom of this complex, multi-layered shield. The question I want to leave you with today is this: understanding the sheer fragility of this system, how will our everyday choices protect the invisible ocean floating right above our heads? I really hope the next time you look up, you see the sky in an entirely new way.